Hi, John Ford. Okay. Oh, hi, Mike. I thought, whoa. Okay, very interesting. Okay, wow. Well done on both you. It's like a back to basics here. Hello, Noel. Hi, May. So, right, apparently. Okay, well, good day to lie, definitely. And good. Okay, yes, yes. And hello, Elizabeth. Hello, Eric. No, no, no. I'm glad you're here. All of you. I mean, I'm glad all of you are here. Hi, Lizzie. Okay, but now here's the deal. It's great to see all of you. No, I actually am I think you did it. I think it's a good, yes, I'm excited. Anybody who's here today definitely picked a good day to be here. Okay, so here's the deal. I'm very glad to see you all. I'm going to try to cut straight to the chase, even a little bit better than usual. Here's the deal. It is our, okay, I'm going to ignore that. Okay, you guys can keep going in the chat, but today's our last day of class. I'm going to be very sad. I'm going to miss you guys. I want again to remind you to feel free to reach out after this for recommendations or support for your future in any way. Seriously, blah, blah, blah. You have my phone number. It's not going to change. You have my email address. It's not going to change. I want to reassure you again, and I'm going to say that I'm going to be quick. I mean, I'm going to be a little bit intense today, okay? Because it's our last day. The main goal of today is to say, no matter what problems I've caused or imperfections I've demonstrated or whatever imperfections you might have. That is, no matter what midterm exam score some of you still have not gotten back, or some of you got, or whatever, no matter what homeworks you did or didn't do, no matter where we are to this day, today is all of our last chance to, no, I shouldn't say that. Today is a chance to bring everything together and still maximize our group possibilities for everybody to really learn something from this course and get a good grade. Like, I want to make very clear, because I'm going to be intense today, not mad, but intense. I view today as the day. Some of you have still not gotten midterm scores back. I know that. That is totally my bad. I want to do everything I can to compensate for that reality. I think all of you who did the extra credit thing, whether the extra credit 14-point thing, I think all of you did that, got your points back. If you know, some of you got like 12 points or 10 points if you didn't like have a final answer or something like that, or if it was late or something. But all of you got some points on that. Whatever points you got on that are literally added directly to whatever score you will end up getting on your midterm, even if you still haven't seen it, which I know, and I'm going to say this again, but I'm not going to say it a million times today. I know some of you, many of you still have not seen your midterm score. I know that. That's pathetic on my part. It's outrageous. It's just, it is the case. I'm going to say again also that there is a final document, which we're going to spend the rest of today talking about as soon as I get rolling here, which everybody has to do. But again, it's meant to help you in the end of the day, whatever score, if you got better on the midterm, once I finally finish them all, that will count more for you. If you did really badly on the midterm, then doing well on this final document that's going to be posted, or that is posted, then that will count more for you. Let me rephrase one final way for all of you. I'm not perfect, and I apologize, to say the least. I've made some major mistakes and caused some anxieties not returning certain things in this class. I'm aware of that. And some of you have had some bad days, perhaps, that I don't know about. But what we're here to do is find the best that you have to give me, and to give me the best opportunity to work with your best and mold it into education and to a good grade. That is, again, if you do something really good on the midterm, or you did a ton of class participation and submitted a ton of class participation points, or you did a ton of homework, or you rock this final, anywhere you can do really well, that will help me calculate your grade. And as long as you give me something to work with, I have a mathematical system that will favor your best in a fair manner. That's true for everybody. But whatever is, as long as you've given me something significant at some point in the semester to work with, that will be the most decisive data in your grade. Okay. And hopefully you can treat me with the same indulgence. What do I mean by all of that? What I mean is, momentarily, in a moment or two, I'm going to start giving the final lecture of this course. It will mostly be conceptual. It'll mostly be in English. It won't be very mathematical or very computational. I'm going to attempt to take the concepts of this course and show you how they all come together into one final chapter of one story that ends here. Okay, I'm going to, once I get some logistics out of the way, I'm going to talk at you somewhat seriously for an hour and 5 minutes. It's not going to be mathematically intricate. It's not going to be computationally intricate, but it will be conceptually maybe a little bit challenging. I'm going to say some things somewhat quickly that you may have to think about a little bit when I'm done. But here's the deal. Your final exam will be a series of true-false questions that in a second we're going to check. Hopefully you already have in your box, you have a pre-version of these true-false questions. It's a series of true-false questions, and then one little free response question at the end where I ask you in sort of a half a page to summarize with your own pictures, equations, or words to summarize the facts as we've put them together. So there's one short free response question at the end, but all the rest is true false questions. We're going to check in a moment that that's landed in your Google Classroom box. We're going to check in a moment that you all have access to it. We're going to check in a moment that you can all open it right now and be looking at it. As I blast through my final lecture, I'm going to ask you, this is what I'm saying. Hold on. This is what I'm saying. The final, you'll see it in a minute. You're going to, the final is basically, oh, okay. Thank you. I appreciate it. But the final is basically on fields, on electricity, but the final will ask you to see how our last statement about fields brings everything to the core of the course together. You're not going to have to do a lot of math on the final from anything. You're not going to really have to do much math at all. You're going to have to see how our final statements about electrical fields, in fact, tie us back to all the earlier material. We're going to check in a second that you can open up essentially the final itself. In fact, let's do that right now. Okay, so, actually, okay, in a second, we're going to do that. You're going to have essentially the final right in front of you as I talk for the next hour and 5 minutes or whatever it is, okay? I'm going to be telling you the last bits of material. I'm going to be, whenever it comes to my mind, I'll even be saying like, oh yes, this is a question somewhere in the true false. Find it right now. You're going to be tracking along with me with the true false questions and figuring out the answers as I talk, okay? On Wednesday evening, I will post the actual final exam, which will look remarkably like the document that you should have in front of you right now or in a minute. I will change the order of the questions. I'll change some words here and there, like I'll add the word not or something to some of the questions to flip the answers from true to false, just so that you actually have to pay attention a little bit, so that you don't just like blindly. But basically, the exam that will be posted Wednesday night will essentially be exactly the document that you're going to have in front of you right now. And then I'm going to talk you through right now for our final class. Like, you're going to have to pay attention. I am going to go a little fast. I'm going to be a little intense, kind of like I sound right now. But if you listen to me while I'm talking and find the question, and I'm going to talk in a certain order. Mostly it is the order of the questions are kind of in the order that I'm going to be talking, or at least the early questions are sort of from material early in the semester. And if you start looking at it sort of halfway through, you'll see that I'm sort of talking in the order of the questions. I'm here to make one final point about the whole course. I'm here to give you the last section of the last chapter of the material, which puts it all together. If you pay close attention to me this period and you've got the document in front of you while I'm talking, you should be able to figure out all the answers to that document. You can talk to other people. As always, you can look back at your notes, blah, blah, blah. But Wednesday night, it will be posted. I'm not going to literally post the answers. I'm essentially giving you the answers right now. It'll help to pay attention, but I'll post that document Wednesday night. You'll have till next Monday night, and I'll put the details in the Google Classroom, but please pay attention right now. And of course, I'll post this recording so you can play it back again. But I'm going to post the final exam Wednesday night. You'll have till Monday night to submit it. Again, it's mostly just true, false. It's a Google form. So the one thing is, you won't be allowed to submit it twice or something. So, do take as long as you want, talk to other people, do scratch rough draft versions on a separate piece of paper. But once you're ready to go, then put in the answers, hit submit, hit send. It'll go to me by next Monday night. Obviously, this won't take me very long to grade, and it won't take me very long to turn around and compute your grade. Whatever you do on this will be meant to help you. If you did well on the midterm, including your extra credit, but you tank this won't destroy your grade or something like that. If you did badly on the midterm, but you rock this, then this will severely help your grade. The idea is we're just looking for you somewhere for you to have done well. That will count the most for you. Okay, I know I keep saying that, but what I'm really saying is in a second, I'm going to start the physics. I'm going to start summarizing all the physics that I want you to know by the end of today. Track along with me with this Google Forms. What I will post tomorrow night will essentially be this Google form, just with the order change and with enough change just so that you actually have to pay attention and read the questions. But it'll be this content, okay? In the Google form, as you'll have it in front of you, don't worry about point values or anything else. I didn't set up the point values correctly yet or anything. Just worry about the content. Sorry, last thing, someone's here, sorry. Also note for our very last game turn, our class participation, the very last one about today is worth 15 points instead of 5. I don't mean 15 exam points, I mean 15 homework points, but it's worth 3 times as much as normal just to incentivize you to really pay attention today. I apologize in advance that once I get going, I'm going to be, again, a little bit intense. Of course, you can put questions in the chat, as always. You particularly should put questions in the chat if anything I say is unclear or you want to repeat it or, or something like that. But I'm going to say today, for the first time and the last time, like what I can't really entertain today is questions like interesting questions like that go off on the side, like how does this relate to black holes or something? I love all those questions from you guys. I love how you ask questions like that. Today, I can't deal with questions like that. Today, I've got to close the books on all of this content. So if you have a question that will help us with this content, please ask it. But other than that, hold your fire and basically understand that, again, today, once I get rolling, I'm essentially teaching you the final exam today. And you're holding and you'll be looking at the final exam while I do it. So you can be sort of taking it, rough draft while I go. The exam that you're looking at or the document, the Google form that you'll be looking at while I go is called practice. I mean, it is practice. It's a pre-final. So you're never expected to turn that in. You're not getting a score on that or anything. It's literally so that you can track along and know exactly what to expect in 2 nights. And so that you know how to pay attention, you know what to look for while I'm talking. Okay. I hope that's sort of clear. I'm going to get rolling in a moment. The first thing I want to make sure though, and again, I'm sorry to be intense like this. And again, I'm sorry that the midterm scores never came back to a lot of you. I mean, that is bad. I know that, but again, I'm doing this whole system in part to try to compensate for that fact. Like I know it's super annoying and super distressing that you don't know what you got in the midterm. So partly why I'm doing all of this way is to make your job as unstressful as possible during finals week and to make the possibility of you still ending up with a very good grade as high as possible. Okay. I hope that's sort of clear. Again, today will be a little intense because I'm going to go through this content sort of fast, but it's conceptual. You'll have to listen with your conceptual brain. If it seems abstract, I understand that. Try, but also give it a couple days to sink in. Like let what I'm saying sink in and don't try to hand in your exam to right away on Wednesday night. Like talk to each other, try to get the answers with each other, blah, blah, blah. You'll have till next Monday night, which is the last night of finals week. You'll have till next Monday night to hand it in. And then again, if I see by Monday night any real danger with any of your grades, if I all of a sudden see that someone's tracking for a C- or God forbid, or God forbid a D or an F, I will reach out and let you know or something. Or worst, if I can't reach you or something, and all of a sudden your grade looks like horrendous and there's no time, seems to be no time to fix it, or no time for you to have prepared for that, then at worst, if I can't reach you before CUNY first time, then you'll get an incomplete. And then that just means reach out to me and we're giving each other more time to figure out what happened. Okay, literally, I mean, I've given this speech to you guys before if you had me for 203, but I'm just saying that you will not suddenly just be shocked with some D on CUNY first without any warning or something like that. Okay, that's the last time I'm going to say that. But what I want to ask now what I want to ask now is, can you, if you go to Google Classroom now and look at the most recent posting under exams, I want to know right now, can you, you'll see something called pre-final exam or practice final exam. Can you follow that link and tell me if that Google form comes up and if you can see that Google form on your side? Could anybody let me know if yes or no success with that? It's on Classroom. Yeah, if you go to Google, like it was posted, I believe, I mean, this is what we're checking right now. I believe it was posted this morning on Google Classroom under exams, the most, I mean, it's also in the stream, but you see it. Thank you, Lizzie. Okay, so great. Thank you, Eric. Okay, thank you. So you literally see a Google form. You can open it. You see the questions, like you see true, false questions. That's a yeah. I'm assuming that Lizzie and Eric are saying yeah. Like you can literally access the questions. Yeah. Could just someone else, just a third person confirm what? Yes. Thank you, Elizabeth. Okay. So I'm telling you again. In fact, I'm going to wait, change the view. I want to make absolutely sure of this. Before I get rolling here, again, I know I have about like an hour. Oh, hey, and that's Elizabeth Fontaine's video. Oh, and it's Stephanie's picture. This is like, okay, that's great. It's never, okay. The mere fact that I'm seeing Elizabeth's, that's awesome. The mere fact that I'm seeing Elizabeth's video proves many, many things, not the least of which you see, it is never too late. The whole purpose of all this is it's not too late for me to finish this physics education with you. It is not too late for everybody to get an A. It is not too late for me to finally know what Elizabeth looks like. It's great. And maybe I probably did before, I'm sorry. But anyway, the point is, so I'm thinking you can all see those questions. So can I just get, before I get rolling, can I get a certain like electronic thumbs up or whatever, if you may not like, but if you understand that what I'm about to do is basically give me an electronic thumbs up if you basically understand that that document that you are looking at right now with slight changes will be your final exam that's posted on Wednesday. Thank you, Eric. Thank you, Stephanie. Thank you, Elizabeth. That's a live thumb. That's awesome. Thank you, Noel. Thank you, Lizzie. That's a live thumb. That's awesome. Thank you, Eric. Or I said, thank you, Stephanie. And thank you for having a picture. And by the way, that like Elizabeth and Stephanie, don't forget that you can submit that. Also, it's not too late to submit those things for points that you submitted a pic. You got what I'm saying. Hopefully, the game turns. It's not too late for any of that stuff. Like wherever you can find it, you can still get points, submit them. And wherever I can find that I can still give you points, I'm going to find them. It's just, we all wish we could have seen the points earlier, but they're going to happen. So if it's clear to all of you, I think, or clear to most of you, I think, that you're looking at essentially your final exam, then again, the order will be changed, like a couple of words will be changed, but that's okay. I'm looking at, there's a direct chat thing. Yeah. Yes, Maisha's question about the game, like, yes, the game turns were never meant to be about like ironclad proof. They're to be like about reminders or indicate. So yes, the answer is yes. Yes. Yeah. Okay. So yeah, again, I'm going to start in a second, but the across the board point to everybody, whether you want to consider this, however you want to consider this, is just like in the next week, you're going to try to do this final exam that will be posted tomorrow. Again, with whatever methods as usual, you could talk to people, blah, blah. You're going to try to submit to me whatever points you still find that you want. And you're going to assume that I'm just as interested as you. If there's a way legitimately, according to the system, for you to get an A or an A minus or whatever, then you're going to get it. Like I'm going to, again, I'm going to favor the things that you did better more. Right. So you just give me the seeds to work with and I will try to grow them into an A flower. We're both just as long as we got. And the flip side of that is, again, that I know it would have been nicer if you saw all the calculations prior to this moment. And you still might never see all the calculations. Hopefully you will, but just assume that anything you do still is going, or that you've done has gone somewhere into the bank of A production. Okay. Similarly, I'm going to assume, I'm not going to assume, I have evidence that you've been trying to learn physics the whole way through. And now I'm trying to put together the physics story for you in this last day. So here we go momentarily. You please have that document open with you. You'll notice that some of the questions at the beginning of the document relate a little bit more to the beginning of the semester. I know that, and you know that. You'll see how they relate or how they come up once I start talking. But probably where I'm about to start talking probably begins somewhere in the middle of the document, if you like, roughly. But once you find a question, once you see the first question that relates to anything I'm saying, then from there on in, pretty much you'll find the questions pretty much in more or less in order of how I'm talking. Okay, so I'm just going to talk in narrative form. The questions are to help you focus on what kind of information you're looking for and what I'm saying. Obviously, everything I'm about to say is going to be true. Those questions are true, false. So anyway, you get it. All right, so here we go. Here we go. Okay. Everything we've been talking about recently, the main subject that we have been in for the last couple of weeks, the main subject we've been in is electrostatic fields. Okay. An electrostatic field is caused by a bit of charge existing somewhere in the universe. While it takes two, and here comes a question that's somewhere in the true false thing. While it takes two objects to create a force, right? There's got to be one mass pulling on another mass in order for us to say that there's a gravitational force between them. That's a question somewhere. It's not the first question, but it's a question somewhere in there. While it does take two objects at a minimum to create or to show the existence of a force, it takes just one object, one bit of mass or one bit of charge to create a field. Okay, that's one of the questions. Look for it. It might say it false, it might say it true, but it is one of the questions. If you have a bit of charge anywhere in the universe, it creates a field. The field is represented by lines that radiate out in all directions from the charge. If the bit of charge, if the point of charge is positive, they'll all radiate in and point into the charge if the charge is negative. Now, what is this field? What do we mean by a field? A field is a patterned collection of information deposited at every and any point in space due to the existence of some object that is in space. That is one of the questions, by the way. A field is, and so if you could find where I am, it'll help you listen for the rest. A field is a patterned collection of information deposited any point and every point in space due to some object that's in space. Okay, that's one of the questions. So then what do I mean by that? I mean, like, if we have empty space first, we have an empty universe, there's nothing in it. Then if there's no objects in it, then there's no objects in it and there's no information in it. It's literally empty. Then there would also be no field lines in it. An empty space is literally empty. If we put one proton in empty space, if we put a point source of positive charge, say, then what we believe at this point is that somehow everywhere in space, everywhere, at every and any point, location in space, there's some information describing the existence of that one charge that's in space somewhere. Like one object alone will create information everywhere in space, information that tells the rest of space that there's an object in space. Specifically, if we put one proton in space, then at every single point in space, somehow there's some kind of number or some kind of arrow or some kind of long line with an arrowhead at the end. There's something there in the point of space that says, hey, there's an object over there. There's a proton of 1.60 times 10 to the negative 19 coulombs of charge, and it's exactly over there, like 14 miles away, 34 degrees to the northeast, right? Like somehow right, that's good. Yeah, the electric field, that's actually really good and helpful. The electric field is like a snitch. It is, that's good. It's a snitch. The electric field is the mechanism by which any random point in space over here learns about or knows about or accesses the vital stats, the data, the information describing what's going on over here at this point in space. And when I say what's going on, I mean the magnitude and the location, the position, the displacement away of some bit of charge, in this case of electricity, okay? So if there's charge over here, space over here knows it and knows how much there is and knows exactly where it is. Specifically, if there's charge over here, like in the center of this like stupid diagram, but it's not stupid, but the simple diagram, if there's a point of charge over here, what those arrows are saying is that if I were over there, if I, like we're just sitting there, if I were to imagine or hypothesize a 1 Coulomb point of positive test charge sitting there, then it would be pushed away, like that way. It would be pushed by the source charge that's in the center of the page. It would be pushed out in precisely the direction of some arrow connecting the two of them, and it'd be pushed out with a force of a certain number of newtons. In other words, the arrows are meant to indicate the direction and magnitude of the force per charge waiting to happen. The number of newtons of force that would be exerted on each 1 Coulomb of positive charge that could be located in any particular spot. If force is measured in newtons, field is measured in newtons per coulombs. It's how many newtons of force are waiting to be exerted upon each possible coulomb of charge that might be at a certain spot. Okay, now the way we imagine this field, the way we imagine this information that's being deposited everywhere, this information that somehow indicates magnitude and direction of force waiting to happen, the way we represent it in our minds and on papers with these lines, these infinite arrows called field lines. And the arrows are based on vectors. They're ultimately, as we discussed last week, these arrows are formed by taking a bunch of vectors and connecting them all up in one long line. The arrows indicate direction. Clearly, they indicate direction. And if it were a negative charge that we had at the center, all the arrows would be pulling in, because the arrows are indicating which way a positive receiver of force would be pushed or pulled. So a positive would be pushed by a positive source, and a test positive would be pulled in by a negative source. Anyway, the arrows indicate direction, and the spacing of the arrows indicates magnitude. That is to say, you notice close toward the center of this picture right here, as you get really close to the plus Q, the point source of charge, you notice the lines are all very close together. They're very dense. There's a great many lines per unit area on the page. That density indicates high strength, high magnitude of field. And of course, field is inverse R squared. It's KQ or 1 over 4 pi epsilon naught Q over R squared. So as you get farther and farther away from that point charge, the lines get farther away from one another, indicating a less and less magnitude. They get less and less dense. There's fewer and fewer lines per unit area on the page. That indicates weaker and weaker or lower and lower magnitude of field strength. Okay, so again, let me just say the last time, and I'll move on. Orientation of lines indicates direction of field. Density of lines indicates magnitude of field. So the field lines are how we are what we imagine existing everywhere in space. But when I say density, okay, I think I understand John Way's question. I think it's a good question. When I say density, I mean how close together the lines are. The more lines there are in a bit of area on the page, that's what I mean by density. I don't mean how thick the lines are. I mean how close, how many there are per unit area is what I mean by density. And so the more there are, the stronger the field is. So the field, I don't know if you could see the cursor on my, I don't know if you could see the cursor on, you can't, I guess, but as you're close to Q, all the lines are close together. There's many of them per unit area. So that indicates that the field is very strong when you're close to the point source, and out on the periphery where the lines are far apart, I would say they're less dense, and therefore the field is weaker. Now, let me say more about this. This may also answer Zhao Wei's question. The picture is supposed to indicate magnitude and direction. The picture shows it to you on a qualitative, comparative, sort of approximate level. But if you do, yes, density means density means how close the lines are to each other, yes. And therefore it does mean how strong the field is, yes. The only one that is correct, Zhao Wei and everybody else, good question. The one correction I would make is right now I'm talking about the electrostatic field. I haven't yet said anything about the magnetic field. I'm talking about the electric field, but that just might be a typo or whatever, just to make that clear. So we're talking about the electric field here, but yes, other than that, yes. Now, the picture, the field lines show you qualitatively how the field is directed and how strong it is. But now, if I were to draw those lines very precisely, and if I were to generate them with like a computer and with a strict scaling factor, like if I were to draw one line for every coulomb of charge or something like that, and I were to draw them, symmetrically and carefully, then we can even use those pictures to actually figure out quantitatively, precisely how strong the field is in any spot due to some source of charge. And we can, in other words, the field is not just a rough concept. It's a very specific numerical piece of information. It's a function. It's a vector function. You name the position in space, and if I tell you the field there, what I'm telling you is precisely how many newtons of force would be exerted on every coulomb of charge there, and in precisely what direction. In other words, the field, there's a precise numerical vector answer for what the field is at every point in space due to some charge. If you want to actually figure out the numerical magnitude and direction, the quantitative magnitude and direction of field at every point in space, you either need really precise drawings like done by computers, and or you need the equation E equals KQ over R squared. Now, here we're about to get to a question in the multiple choice, in the true false. Like, if you want to get the numbers of how many newtons per coulomb the field is, you either need to use that value K equals 8.99 times 10 to the 9th Newton meter squared over coulomb squared. Or you have to realize that K, in fact, is a shorthand for 1 over 4 pi times that permittivity constant epsilon naught, which equals 8.85 times 10 to the negative 12 coulomb squared over newtons times meter squared. Here's what I'm saying, and this is literally one of the questions. And the answer, if you find the question that has to do with K and epsilon naught, I'm telling you right now, if you're paying attention to me and you're tracking with me, telling you right now the answer to the question, if you find it, is false. What I'm saying is you need either K is a shorthand for epsilon naught, and you need one of those numbers in order to numerically figure out the actual value of the field at any, if you're actually doing calculations. The calculations are based on the amount of charge, the distance away, and that constant of proportionality, which is technically epsilon naught equals 8.85 times 10 to the negative 12. But there's a shorthand for it, which is K equals 8.99. Now, I'm not telling you to memorize the numbers. What I'm saying is I need you to know that you need that number epsilon naught. It's a universal constant. It's a constant of proportionality that gets you the electric field, just like capital G gets you the gravitational field. So that question, that wherever it is in the true false that says like we don't that the electric field doesn't depend, it depends on neither K nor epsilon. The question says something like that. No, that's false. It totally does depend. Okay, I don't remember which question it is, but if you're tracking with me, the actual numerical value of the electrostatic field does depend on that epsilon naught number, that universal constant, 8.85 times 10 to the negative 12. Just know that. Now, I'm going to switch screens for a second and remind you and show you, like, field line pictures can be drawn more precisely than my hand. I mean, they can be done on computers and all that kind of stuff. And the reason field line pictures are so important and field line calculations are important is that in the real world, in real situations, we can have more than just one point causing field. We can have 2 points next to each other causing field. We can have 3 points next to each other. We can have 2 points that have the same charge. We can have 2 points that are equal and opposite charge. We could have a whole tube of charge or something. Charge can come in any kind of complicated shape. And then that shape of charge will tell the rest of the universe, will tell all of space, here we are, we're in space. Like, you got to know that we're snitching, like you over here, you point in space, you got to know that we're over here causing charge. And if you put some test charge over there at that other point, you're going to be pushed or pulled by us in a certain kind of way. So whatever charge you put anywhere in space in any kind of shape is going to produce field lines that tell the rest of space that there is charge somewhere. Right. We went over. Right. And the more complicated the picture of charge, the more complicated the field lines. Let me just see what John's saying. Yeah. Oh, good. Yes. Oh, very good. You did. Very good. Yes. I almost forgot. Yes, you did. So good. So that's helpful for this. So I'm going to switch screens for a second and remind you. Yeah, okay, here we go. Okay, you could, yes, if you see on your screen now, I'm looking, okay, yes. If you see on your screen now in the middle, these are just random examples from like Google Images. But what, yeah, this is coming through. Okay, what I want you, and I'm reminding you, and yes, you did something like this in the board meeting in lab. But if you look, like all the way to the left is the field lines caused by a dipole, by an equal but opposite pair of charges, right? All the way to the left. In the middle is two equal like charges, two positives causing field lines. All the way to the right is a positive and a negative next to each other, but the positive is a much stronger charge. It's like, 5 coulombs, whereas the negative is just like 1 coulomb or something of negative charge. These are just examples of the field lines caused in space by various configurations or distributions or shapes of charges. Am I asking you to memorize these pictures? No, no, no. Am I asking you to draw pictures this complicated yourself? No, no, no. What I want you to see, what I want you to really take seriously is that, like, these pictures are elaborate. They are certainly elaborate. They're certainly fancy, and they can get very complicated. In fact, one thing I want you to see is the more complicated the shape of the source is, like the more complicated your configuration of charges, the more complicated the field line picture will be. For sure, they can get very complicated. But please also notice, they never are random or weird. All these field line pictures are all in their way, look very patterned and very smooth, and in a way, sort of simple. They are always only as complicated as the shape that's causing them is. In fact, that's, a dipole. No problem, direct chat person. And wait, a dipole is a temporary charge, right? Well, dipoles, they don't have to be temporary. I mean, that's a good question, but dipoles don't have to be temporary. I mean, I think I understand what you're saying, but even technically, like a hydrogen atom is a dipole. I mean, it has 1 proton and has 1 electron, and they're nearby each other, and they're equal and opposite in charge. So a dipole doesn't always have to be temporary, but what it is well, yeah, is like a pair of equal and opposite charges, and it creates field everywhere in the world. What I'm saying is, please notice that the field lines snitch, like John said, field lines, like, can you see? Yeah, you can see my cursor. Like The whole point of this field line picture is that if I go to some point in space, like where the cursor is right now, I would be pushed. If I were at that point in space, I would be pushed in a certain direction due to the presence of the positive very close by to me, but then there's also negative a little bit less close to me. In other words, if there were just that positive there, I'd be pulled on a straight diagonal line, like whatever line you could imagine connecting the positive charge to my cursor arrow, I would just be pushed directly along that line due to the positive. But because there's also a negative there pulling on me toward it, I'm pushed along a slightly skewed direction, the direction like tangent to the curving field line right there. Or what's another example? But I'm not pulled or pushed that much. How can I tell not that much? Because there aren't that many field lines over in this region where the cursor is. Over here where the cursor is now, there's a lot of field lines. The field lines are very dense. I would be pushed very hard somewhere in that region. If I were like right in between the positive and negative, the positive would be pushing me very hard to the right, and the negative would be pulling me very hard to the right. So there'd be a really strong field there, and that's why the lines are so close. What am I trying to say? I'm trying to say, and here comes a question in the true false. I'm about to say something that you'll see is one of the true false questions. I'm saying, as fancy as these field line pictures work, I mean, as fancy as they look, they're only ever as asymmetric. They're only ever as complicated, or in fact, they are exactly and only as complicated as the shape of that which causes them. In fact, that's their point. The way that if you're anywhere, if I'm somewhere in space and I'm in this complicated picture all the way, number C, if I'm somewhere over here where things are really, really fancy, really complicated, the point is that really complicated picture right in space where there's all these arrows close together and they're sort of all curving this way. That's what tells that point in space, yo, you're nearby not only two charges, a positive and negative, but the positive is a lot stronger than the negative. Like this, in other words, it's a one-to-one correspondence between the asymmetry, the complexity of the source, and the asymmetry of the lines. For every one shape of charge you can imagine, it will produce exactly one field line picture. And it works in reverse. If you're in a field line picture, if you know these pictures well enough, you know what's going on in space causing that picture. So I'm saying, let me say it one last time, field line, the pattern of field lines is always exactly as asymmetric as the shape of the charge source causing the field lines. That's how, so field lines are a picture that go everywhere in space to tell everything in space what's going on somewhere in space, what kind of shape, what kind of magnitude, and at what kind of position there might be charge somewhere in space. I'm going to scroll a little bit more down. Like, see, like these pictures are simple because they're caused by simple things, like one positive charge over here, one positive point, one negative point over here. Here, this is, we'll see is a little bit weird. I'll talk about that later. But D is whoa. This is a true false. Which of the following electric field lines are incorrect for point charges? Okay, sorry. So like D would never happen because positive charges cause lines to go out. That for those lines to go in, that source would have to be negative. C would never happen. C would never happen because lines are only as asymmetric as the thing that caused them. If one point is causing lines, then they'll go out symmetrically in all directions from that point. So C would be false. It would never happen. F would never happen. Lines never cross. Anyway, I don't want to get too involved, but I'm just trying to say, like, so now this picture right here, very complicated looking, but very possible. It's complicated because it's a dipole. It's a complicated picture due to a complicated situation. But again, please, I'm going to say it one more time, and then I'm going to move on. The field lines are as symmetric as they can be. If we had nothing in space, there'd be no field lines at all in space, pure symmetry. If we had one thing in space, we have lines symmetrically going out of it everywhere in space. Lines are as symmetric as they can be. They're only as asymmetric as whatever's causing them. So we can tell what's causing them. We can tell how asymmetric the cause is by how asymmetric they are. And why am I? So again, here's an example. That's an example. This is a legitimate example of something going on in space, right? They get more and more complicated, but they're only as asymmetric as what causes them. Now, why am I saying all this? What's my actual point? But again, that was one of the questions in the true false, what I just said. Why am I saying all this? Because what I really want to ask in the next 30 minutes, 29 minutes, I know we have 29 minutes, what I really want to get at, the final question of the course is, what happens when the information gets updated? What happens when this picture changes? In other words, any one of these pictures is the picture of the universe, the picture of the lines all through space. Any one of these pictures is the picture of information everywhere in space, describing what's going on right now in space. Like there's a charge over here, there's a charge over there, there's a charge over there. These are the lines. But what happens if a charge starts to move, or if we add charge somewhere? What happens if the thing causing field is dynamic? If it's subject to change, how does this field of information, how does this collection of information throughout space get updated? That's my question. I have 28 minutes to answer it. Here's what I'm going to say. Here's what I'm going to say. If we had, and I don't have a picture for this on the board, you're just going to have to bear with me. Well, actually, yeah, okay, wait, I'm going to switch my board. Bear with me, I'm going to switch the board so I can draw something for you. Hang on. Okay, so that was it. Okay, this is like a dipole, right? Now I'm going to give you a new example. What if we had, all right. Imagine if you had a line of charge, okay, a proton, 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 all sitting in a line. That's the black line there, a line of static charge. So a bunch of protons all together, just sitting there, right? If you think about it, each one of those protons would create field lines that would radiate out in all directions, like up, down, out, in, left, right. But then the charge right next to any one given point would do the same thing, up, down, in, out, left, right. And like the right arrow from this guy would cancel out with the left arrow from the next guy, right? And all the arrows going horizontally along the x-axis, if this line of charge were along the x-axis, all of the field lines along the x-axis would all cancel each other out. And what you'd have left is a bunch of lines spoking out. Now, this is a cross section, it says. Like you'd have a bunch of lines pointing up, a bunch of lines pointing out, down. You'd also have lines pointing out. You'd have lines radiating out in all directions except for along the x-axis, right? In other words, it'd be like a big caterpillar with legs coming out all from it, right? Hopefully you can see that. So I'm saying a line of static charge Yes, that's good. Yeah, it is kind of like how solids work. That's good. Like a tube of charge would create. Yes, that's good. So a line, a one-dimensional like axis of static charge would create field lines that would radiate along all axes except for that one. So they'd be like spokes, right? It wouldn't be a star burst anymore. There wouldn't be things bursting that way, but there'd be lines bursting every other way except that one. Spokes, okay? That would be a line of static charge. Again, why? Why am I saying that? How do I know that? Because those lines would be exactly and only as asymmetric as the line itself. Like the line says, hey, we're charged everywhere on the x-axis. So the field lines would say, okay, let's point the same way in all directions except for the x-axis, right? Just like one point would make a star burst in all axes, a line would make spokes in all axes but that one, okay? Similarly, if it helps to picture, if you made a plate of charge, it would produce lines coming out. If you made a plate of charge in the XY axes, then it would have lines coming out up and down only along the Z axis. The lines are always as simple as they can be. They're as symmetric as they can be, only as asymmetric as the thing that caused them. The lines tell space over here what's going on by showing a difference, an asymmetry, an oddness, a complexity of what's going on over here. I'm saying all that because if we instead, okay, so this is all static situations. This is how field lines work in static, like moment to moment situations. If instead we had
Professor,
yes.
why is the line between the static charges in opposite directions?
Why is it in it? Wait, why is it what?
The line from the static charge.
Yeah.
The static charge line.
Yeah. Why? Yeah. What? Yeah. But what about it? What's the question about it?
Yes, because the charge is from different direction, is from opposite direction. So what means that?
No, I just mean, wait, I'm not sure. I just mean, like, imagine that the line goes on forever. I mean that it would create field going in all, I'm not sure. I'm just saying, imagine it's a long, long line of like proton, 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 proton. I'm saying all of those protons would create field lines going everywhere.
Oh, okay.
Oh, okay.
Oh, okay. So it's a proton line. So
Yeah.
okay.
Okay, cool. Okay. So, but now I'm saying to everybody, here's the tricky, the important, and I'm watching the clock, I promise. I know we have 21 minutes. Now I'm saying, what if we have a flow of charge? And this is getting now to the next questions in the thing, if you find where I am. I'm saying, like, what if we had a current? What if we had like a long line of charge that's actually flowing in a particular direction, like this, right? Now, this is interesting because, well, or even if you just have one charge for a minute, if you have one charge move, if you have one point charge, it creates the field lines radiating everywhere out from it. But if the charge moves, then those field lines like move with it, right? Like they were all bursting from here. Now they're all bursting from here. So all the lines would have to shift somehow. And so there'd be a shift in the picture. If it kept moving like that, the picture would keep shifting. And if we had a continuous flow of charge, a current, right? If we had like a stream of charge, a river of charge that kept flowing, 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 then there would be continuously a change in all these radial lines. They would be continuously like flowing over here, but somehow the whole picture would have to even out in the end. If you look at a flow of charge like a river, it's always flowing, but it's always flowing, right? Like a current in your lab, like in your labs, if you look at a whole bunch of a line of protons that's continuously flowing, then it's always in motion, but any given moment you look at it, there's always protons right in front of your eyes, like a river. There's always water right in front of your eyes. It just keeps flowing, flowing. So it's like constant velocity motion. It's velocity, it is motion, but the motion is stable. So the picture would be very different. The picture would not just be a bunch of spikes anymore, a bunch of spokes. Somehow the picture of lines would have to indicate that everything was flowing to the, in this case, to the right. But if it's always flowing to the right and always flowing at the same speed, the picture would have to stabilize somehow. There'd be a stable picture of field lines that somehow indicate that no longer do we just have a point, but now we have a line, and we have a line with direction. In other words, somehow the field lines would fall into a pattern that indicates this vector of charge. What would that pattern be? I'm asking rhetorically. I'm not asking you, but I'm saying, if you think about it, field lines would have to fall into a new pattern that indicates this pattern, this constant change that's going on. Well, the pattern would have to follow the rule. The pattern of field lines would have to be only as asymmetric as this situation. There'd have to be a nice clean pattern of lines that somehow is clean and simple and smooth, but somehow indicating to the universe that there's a line somewhere and the line has direction. The field lines couldn't spoke out of this line. They couldn't just spoke out of the line anymore. They would spike out of a static line, but they couldn't spike out of a moving line because there's no way the spikes would be able to tell us whether the motion was left or right. There'd have to be some kind of pattern of lines that indicates there's a charge flow in a particular direction. And what the simplest, smoothest picture I could possibly imagine, or we can imagine, of field lines that would indicate to space that we have a flow, in other words, a constantly changing situation, would look like this. And I'll change the screen again in a second. The field lines would look like this. What I'm saying is, and this is a pretty bad picture, I'll show you a picture on the computer in a second if I can. I'm saying that the simplest, smoothest, most symmetric picture you can imagine, or that could exist, of field lines generated by, caused by a vector of charge, a current, the simplest, most symmetric picture of lines you can imagine would be closed loops, closed paths, field lines that don't radiate out from some source and go to some sink. No, we would have lines that would loop around themselves, that would form circles, concentric circles, looping around the wire, getting farther and farther away, like extending out to infinity, like lines are supposed to do, getting less and less dense as we get farther and farther away from the source, but they would loop around the source rather than spoke out the source. In other words, I'll say one last way, and I'll try to show you a picture on the web that might be clearer than mine. I'm saying if we just had one charge point sitting still, it would create field lines that radiate out from it. Symmetry, symmetry. If we had a line of charge, it would create spokes going out of it. Symmetry, symmetry. If we have a vector of charge, a current, picture my thumb, then it would create lines that would loop around it a la my fingers. And the fingers would loop this way to show that the current was going that way. If the current went the other way, then my fingers, the field lines, would loop the other way. In other words, we get these loops that are symmetric, that loop around the current to show us a current is there. Lines are always supposed to show us where the thing is causing them. But instead of radiating out, they would loop around, and they loop around in a certain direction, indicating the direction of this current. Let me see if I can quickly give you a picture on the web. Hold on, and bear with me for a second, because I know we're almost done. Oh, and I'm going to hit return and switch the screen in a second. But what I'm saying here, again, I'm saying if you understand that field lines are a pattern of information in all of space, indicating the presence of something in space, then the field line picture is always the field line picture is always symmetric as it can be. It's only as asymmetric as whatever's causing it. So if you have if you have a changing picture, if you have a flow of charge, so the charge is always flowing in a long straight line, we call that current. I'm saying that's a sort of constant change. It means that the electric field is changing all the time because we've got all these charges moving all the time, but it's changing always in the same way. So we must get a new picture that isn't the same as the old picture, but there must be some sort of stable picture that represents this stable direction of flow. The simplest, most symmetric, stable picture I can imagine around a long straight flow is concentric loops, circular loops of field line. Those field lines that loop around a long straight current are often called magnetic field lines. That's what magnetic field lines actually are. They are merely the change in the picture of E field lines that comes about when we have, instead of one point of charge, when we have a flow of charge or current. So with that said, I'm going to show you the picture, what I'm talking about. Yeah, yeah. Yeah, okay. I'm going to switch screen. It's coming, I'm switching. Okay, hold on, I'm switching, bear with me a second. And I know we have 12 minutes. Oh, this way. The direction of the current is the opposite direction. Well, in this case now, I mean, I think this is a really good question, Stephanie. In this case now, I'm saying the current is the item. Like, so I'm saying that I think this will, I'm saying now, if we think of the current as being the item, it will cause field lines like, yeah, like if you, like this thing here with the, look at the picture with the hand and the thumb. I'm saying if you had current going straight across the page, it would cause lines to loop around it at every single point. Like they're just drawing one particular section of it, but at every section you'd get these lines that loop, that form circles going around the straight line, and they get farther and farther away as you get, I mean, they get farther and farther away from one another as we get farther and farther away from what is now the item. The source is now a current. Okay, so what I'm saying to everybody, and again, this is one of the questions in the true false. I'm saying if a point of static charge just sits there, it creates a symmetric picture of field lines radiating out from it everywhere. But if you have a flow of charge, it creates, by the same rule, by the same understanding of field lines must be as simple as they can be, or as symmetric as they can be, given the complexity or the asymmetry of the item causing them. If the item causing them, if the source causing them is a flow of charge, then you'll get field lines that symmetrically wrap around or loop around that flow. And everywhere you're in the circle, you, like if you're in one of those circles, you could tell if you fought, like you could tell, aha, I'm looping around on it. There must be an axis. There must be some flow at the center of my circle. If I'm looping like this, then the flow is in the direction of my thumb. If this way, if I'm flowing like, if the field lines are looping like this, then the flow must be the other way. These are called magnetic field lines. And not that you even have to memorize that, but magnetic field lines are just the new type of picture of field lines we get when what's causing the field is a long flow of charge rather than just a sitting point of charge. In other words, these looping lines are what we get. They're the simplest, most symmetric lines, the most symmetric way for space to read the information. If what's causing the field is a vector rather than a point. Okay, so one last way I'm going to say it, and then I know I have 10 minutes. I'm saying that that a flow of current is a change in the electric field, but it's a change that is itself constant and stable, just kind of like constant velocity is a change in position, but at a constant rate. A flow is like a changing electric field, but in an ongoing, reliable, constant, steady flowing way. So it creates a new picture of the field lines, but a steady, stable picture that looks like these loops going around rather than these starbursts. Okay, these magnetic field lines can be calculated, like the strength of what this is called the magnetic field can be computed numerically with as much precision as the electric field can. Here comes a question in the true false. Well, when we're computing the magnetic field, this field of due to flow, due to current, rather than due to static charge, instead of using that epsilon naught number, that 8.85 number, we use a different number for this field called mu naught, which is like 1.26 times 10 to the negative 6 henries per meter. That's one of the questions. I don't remember if it's phrased as true or false. I think it's phrased truly in the thing. But if you look at one of the questions, it is the case that when you're computing magnetic field, instead of using the epsilon number that we use for electric field, we use this very similar but different number, mu naught. Okay, so epsilon naught is the universal constant for the electric field. Mu naught is the universal constant for steady changes in the electric field known as the magnetic field. Now, we only have 8 minutes, but we're almost there. What I want to say now is, okay, we have 1 point of charge, it causes radiating field lines. I'm going to turn off the, okay. If we have 1 point of charge, it causes field lines that radiate out symmetrically in all directions. If that picture starts changing, if the charge starts moving along so that those arrows have to move along, if we have a whole bunch of dots all marching along, all flowing along in what we might call a current, then the lines all fall into a new formation where they loop around that current. If now we make that current change, like if now we have a change in the change, kind of like acceleration, right? If you imagine being in the lab and causing a current where you're slowly turning up the current value in time, like the dial on your power supply. If you started turning it up in time so that we not only had flow, but we had change in the flow, then what would happen? Well, then all of those lines of field that were looping around the flow, well, they would now be like little currents, right? They would have a change going on. So they would change the picture. What would happen? Oh, I'm going to turn off this switch. Sorry. What would happen? I'm just turning off the other screen. Okay. What would happen? Well, by the same logic, and follow me this, we've got 6 minutes left. We're almost there, but just try to stay with me. This is all really about derivatives and rates of change and patterns, stuff like that. If you have 1 point, it creates bursts. If you have a flow, it creates loops going around the flow. But that's if it's steady flow, you have loops steadily going around the flow. If the flow starts changing, like if your current is some linear function of time, then the change has a change. So these loops will in effect be flowing. They'll be changing. So at every little segment of the loop, this is one of the questions, you'll get a loop around that. Like if I have flow, right, this is all about the right-hand rule, totally, yes. And I'm going to ask you guys, since I only have 6 minutes, I'm going to ask you to maybe hold your questions to right to the end from here on in so I can get to this. But yes, totally the right-hand rule is what I'm talking about. So if we have flow going like this, like my current, if my thumb is the current, you'll get lines of field looping around it. If the current isn't steady, if the current is getting stronger and stronger in time, then these loops will have loops going around them. So one loop like this will then cause loops going perpendicular to it everywhere around it, because it is now like a little current in space. So it will cause all these loops around it. Now, right, literally, we can have loops and then perpendicular interlocking loops caused by that. Like you'll have like magnetic field, like a loop of field causing a new loop of field. Now, if your current, and we're just about done, say your current is just like an algebraic function of time, like your current is like 1/2 a t squared or something like that, then you could take a derivative of it, you know, and get a new loop. Maybe if it's quadratic, you could even take another derivative of it and maybe even get another loop. But as long as it's an algebraic function of time, as long as it's like one quadratic or linear or cubic, as long as it's t to some finite power, eventually you take enough derivatives, you don't have, and you'll get a constant function. You'll get zero. This is one of the questions. I don't remember if it's true or false, but like literally, if current is like a quadratic function of time, then if you take a couple of derivatives or three derivatives, you're eventually going to hit a constant. In other words, a quadratic function of time current might cause a loop, which might cause a loop, which might even cause another loop, but then that's it. That's all the loops we have. End of story. If, and we're almost done here, if, however, going back to the beginning of the whole year, semester, if, however, you create a flow of charge that is some sort of non-algebraic function of time, like a cosinusoidal function of time. If you create flow of charge that has a derivative, which has a derivative, which has a derivative, right? Like cosine, the derivative is negative sine. The derivative of that is negative cosine. The derivative of that is sine. And it keeps going on and on forever, right? You can take derivatives forever. If you create a current for which derivatives can be taken forever, then you're going to get a loop that creates a loop that creates another perpendicular loop that creates another perpendicular loop, and the current will keep going back and forth. These loops will keep going back and forth and being sideways, up and down, sideways, up and down, sideways, up and down. And the loops will keep creating loops without limit. That's one of the questions. It is possible to create a flow of charge that is infinitely differentiable, that creates loops, which we create of field, which create loops of field, which create loops of field, which go out forever without limit in space from the original thing that caused them. You can create loops, in other words, that oscillate back and forth and oscillate back and forth and propagate off in the manner of a wave. We have 2 minutes left. Let me say this really important thing. Number one, it is, and this is one of the questions, it is possible then to create like a cosinusoidal current or something like that, that creates electric field lines that loop around themselves and oscillate back and forth and satisfy the wave equation. It's possible to create electric field that could be written in the form of the wave equation. And remember the wave, so that propagates off according to our wave equation. And remember the wave equation is second partial time derivative of something is directly proportional to second partial space derivative of something. And the constant of proportionality is the speed of the wave squared. In one of those true false questions, it says what I just said, but it says like, is the acceleration of the wave? That's false. The square of the square root of the constant of proportionality in some wave equation is the speed of the wave squared. What I'm telling you right now is if you create an electric field that changes itself, it'll create loops and loops and loops that go out forever and propagate off in the manner of a wave. The wave equation can be written, the constant of proportionality is 1 over mu naught times epsilon naught. Though if you type in those numbers into a calculator, you will find that this, and I've got 1 more minute, just bear with me for a second. I am saying if you create current that's cosinusoidal, it will create loops of field lines that will reinforce each other, reinduce each other, and fly off like a wave at a speed of 1 over the square root of epsilon naught times mu naught. If you type, you don't have to do it now, but if you test on a calculator 1 over the square root of mu naught times epsilon naught, that is what turns out to be the speed of light. What I'm saying is that this is what light is. Light is a wave traveling, is an update of electric field information. It's how new information in the electric field travels from one place to another. When a change ever happens in the world and space finds out about it, that new information leaves the source and travels to points in space in the manner of a wave, in the manner of electric field lines causing other electric field lines, causing other, in other words, and I know there's like 30 seconds left, I'm saying this, what light is a wave. It's a ripple in the electromagnetic field. And And on the one hand, the thing that makes sense is just like sound waves are immaterial pulses that we believe in because they're caused by vast collections of material particles harmonically oscillating back and forth to create this pulse. Light is a pulse that is caused by a vast collection of little field loops oscillating back and forth and sending the pulse. It all makes perfect sense, except the thing I want you to understand is that sound is information that we believe in because it's pulsing through material oscillators. Light is information updates rippling through a vast collection of field lines, and field lines themselves from the start were just raw information. So light is a pulse, is a ripple in a field of raw, pure information. Light is the universe updating one point as to the information that just got changed at another point in space. Light is updates in physical information. Light is an immaterial pulse propagating through the immaterial medium known as electric fields. That is what light is. That's the course. That's the questions in the true false. Like if you, it's a lot to sink in, but if you let it sink in, if you talk to each other, you'll see that the answers to all the questions in the true false that I just, gave to you are all contained in what I just said. You can obviously replay the video and all that stuff. But as long as you answer those questions and then try to submit like a half-page picture or a couple in sentences and equations of what, then that's it. That's the final, and that's it. Now I'm gonna stop. We're done. You can go. I owe you a lot of stuff. You owe me some now, a little stuff. I will post all this in Google Classroom. You've been an awesome, awesome class. I really enjoyed you. I'm gonna hang out for a second if there's questions, but I don't want to keep anybody. So okay, thank you. But thank you all very, very much. Thank you all very much. I will hang out for a second if there's questions, but that's it. That's the course. Okay, thank you. Thank you. Thank you. Okay, I'm turning off the recording also.